I got here a little bit later today. I now have textbooks in my office. I've somehow been here for half a year and have not moved textbooks from my house to my office. So now if anyone ever wants to do things like randomly just borrow and read a book about game balance, whole textbook just about the balance of games. All right, so this is the very few slides. There are only, including the title slide, there are 5 slides to this final thoughts. I should have just addended it to the end of the last one, but it wasn't quite the same. It's just kind of what can we do with context-free languages? How can we better understand them? So the first thing we can ask is about the closure of context-free languages. So if you have multiple context-free languages, is the result of taking the union or the intersection is the result a context-free language? Is the result something that's the kind of question we can ask if we take set operations on context-free languages. So they are closed under union. And by that, I just mean if you take 2 context-free languages and you union them together, the result is a context-free language, always. Concatenation. If you concatenate a context-free language to another context-free language, that means each string in the resulting language has a first part that comes from the left-hand side of the concatenation and a right-hand side that comes from the second. So you're not picking one or the other or both, or you're taking 2 possibilities, one from the left-hand side, one from the right-hand side, and sticking them together. And that string would be in the resulting concatenated language. They're closed under star closure, which means if you take a context-free language and you say, repeat any string, take any string from this language and just pick a string from this language. It doesn't have to be the same one, but you can kind of concatenate different strings from this together. Then you end up with a context-free language. So picking 0 or more elements. What have we not covered? What do we think that context-free languages are not closed under? Where you take that set operation and you get a result that is not context-free.
Intersection.
What makes you say intersection?
Just because of briefly limits and kind of simplify the kind of concept of language.
Yeah, so that would make sense. Any other set operation that makes sense that the result would not necessarily be context-free? What set operations are there left?
Like set division.
Kind of. There's a big one we haven't hit yet, though. Not closed under complementation. So you take the concept of a universal set, which is all strings that could be composed of any characters in the alphabet, and you basically do a reverse of everything that was rejected by the context-free language is now accepted, and everything that was accepted is now rejected. You would think that you could just take something like an NPDA and invert the finality of the states and you'd get the opposite, but then that doesn't consider certain aspects of strings that don't start with the same characters out of the NPDA. Because you can stop early, basically, you would need to define some way of inverting the stop early into an acceptance, which we can't easily do.
Sorry, I think these are probably dumb questions. The complementation is still limited to the same alphabet, right?
Yes.
And then can it have multiple complementation? So like if it accepts words that start with A, then in the alphabet ABC, then it can have any word that starts with B or C.
Right. And that would be an example of probably a context-free language, but it's not guaranteed to be context-free. So if it's closed under, that means that no matter what languages you pick, if they are context-free, then they're closed under those operations. The result is guaranteed to be context-free. So while context-free languages are not closed under intersection, a very interesting result happens if you take the intersection of a context-free language and a regular language. That ends up being context-free. That kind of makes sense though, right? Does that make sense? Is there an intuition behind why that might be the case? Yeah,
Isn't it because all regular languages are also context-free languages?
it is a subset, but then you would think that if that were the case, then the intersection of a context-free language and a context-free language would also be context-free, but it's not necessarily.
When you say context-free at the end there, does that exclude regular?
No.
Okay.
And you take the intersection of a regular language and a regular language, the result will be regular, but it will also be context-free.
Yeah, thanks.
Yeah,
If I remember correctly, I might not, context-free languages require like a stack, and I assume there might be at some point where you require a stack. Some part of the grammar, or like while you're doing,
yeah.
the DFA or NEA.
That's actually a really good way to think about it. If you have two different context-free languages, you need two different stacks paying attention to each one. And if you take the intersection of that, you may need to find where you need information about both stacks. Whereas if you have a context-free language with a single stack and a regular language that does not require a stack, you mash them together to say, when are they the same? Or when do you have an element that that's in common between the two, you still only need one stack to keep track of that information. That's exactly right. So yeah, it comes down to the number of stacks that you need to be able to represent the languages. The reason we talk about this is sometimes this lets us get around the pumping lemma. And I think all of you would appreciate whenever you can avoid using the pumping lemma, we want to avoid using the pumping lemma. If we can do something easier than that, we should try the easy thing first. Only go through the tedious, difficult process if it's as a last resort. So here's a language that is context-free. We have a to the n, b to the n, such that n is greater than or equal to 0 and n is not equal to 100. So it's an interesting language, right? You have to have a bunch of a's followed by a bunch of b's, but the number of a's and number of b's can't be precisely 100 each. So think about now, how would you design a grammar for this? What would that grammar look like? Come up with a conceptual version. Do not try to write it down because you won't finish by the end of class. Yeah.
You need to have like 99 different states prior to a 100th state where you won't be able to accept from there, and then after that you can just add any more A's and B's that you want.
Yeah, for a grammar, you need to have a production to be able to generate 0 A's followed by 0 B's. So you need to be able to end with a lambda. You need to be able to produce 1 followed by 1, 2 followed by 2, 3 followed by 3, and they could not interact with each other or self-reference. You'd have to find a way of doing this and then terminate, this and then terminate up to 99. And then you could do 101 and have that loop around to another one of 1, because once we're at 101, we don't care how many more there are as long as it adheres to that form. But getting to that 100 is going to require 100 different productions of A's and B's of different lengths. And that is disgusting. Absolutely disgusting.
So if this was the intersection of two, or context free and a regular language, the like
It
regular
is.
part,
Yeah,
yeah, no, the regular part would be like A to the n and does not equal 100, and then the context free part is we just have the stack to keep track of how many A's there are.
yep.
Okay.
Yeah, the regular part is the n equals 100, basically, where we could very much have a DFA with a bunch of states that read 100 A's and then 100 B's. And if it sees exactly, you just have all of those be accepting states until you reach exactly 100. And then you reject, and then you, on any number of A's and B's that you see, you just loop and accept. So you could identify exactly 100. But the A to the N, B to the N portion is context free. Think about drawing an NPDA for this. What would that look like?
Need another state. That like from all of the A's less than 100. You need all of those to go to a different state on a B, right?
Yeah, there's no way to count exactly the number that you've seen so far without peaking that many times. So that would be gross. Yeah,
You could put like 99 things on the stack if you wanted to, like that little like loop into the thing, you just like add, you can put like 8 to the stack, 2 A's to the stack, 3 8, and you can just do that. And then have a transition state where you go to a next state and then you make sure you put 2 on. And then, so you're like skipping essentially 100 if you want to keep going. And then after that, you can have another state that just says you can add as much as you'd like and then, you know, basically have a final state after that. But it'd be kind of gross with having to put that much. It's really rough. I mean, that's my solution.
yeah. So these will work. These ideas will work, but they're gross and we don't want to draw them out. We don't want to, because if you're going to prove that something is context free, then you could either prove something is not regular with a pumping lemma. You could prove that something is context free by writing a grammar for it, drawing an NPDA for it. But if we know that the intersection of a context free language and a regular language is guaranteed to be context free, if you're interested in the proof for this, it's in the book. You can use this concept of if you can identify the context free portion, you can identify the regular portion, and you can identify the entire language as an intersection of those two languages, then you're just done. There are also fun cases you can use to do this to prove that something is not context free by contradiction. So what would something like this show? That the language of the strings in ABC such that the number of A's are equal to the number of B's are equal to the number of C's. And we're not talking anything about the order of A's and B's and C's in the string. We just need to keep track of and determine that they are equal. First of all, intuition. Why is this not context free? Number of A's is equal to the number of B's was context free.
With only one stack, it's hard to keep track of the count of 3 different things to be equal. It's really easy with 2 because you can just go up and down. With 3,
Yes.
you don't have a third way of
Right.
keeping track of that.
When number of A's were equal to the number of B's, if we'd seen more A's than B's so far, there was a particular stack symbol for that. If we'd seen more B's than A's so far, there was another stack symbol for that. So based on what was on top of the stack, you could peek at what's on the top of the stack, and that paired with the letter that you were seeing told you whether to push or pop. When you have 3 letters to look at, you can't do that. You would have to have some stack character that said we've seen more A's than B's and C's, but then you see a B, is that still true? You see a C, is that still true? We don't know. What would you push back on the stack if you determine that there have been more B's and C's than A's so far? Do you push something that represents that there are more B's than A's and C's, that there are, you're lost. There's no way to do this. So my first step whenever I see something like this is to just take a step back, try to find the intuition, because that intuition will absolutely help you to be able to construct a proof. So we could use the pumping lemma for this. We could do that, but we don't need to. First of all, we can assume that the language is context free, so we're going to continue just like a pumping lemma, proof by contradiction. We want to take the intersection of the language that already exists, if we assume that it's context free, and A star, B star, C star, which is regular. If this language is context free, then when we take the intersection of them, the result will also be context free. Does that make sense? What do we get when we take the intersection of the example language with this regular language, A star, B star, C star? What is that intersection? All strings that are shared in common between these two languages. How would we define that as a language?
Wouldn't it just be the A star, B star, C star?
It is
at the
not.
intersection?
It's close. But A star, B star, C star says nothing about the number of A's and B's and C's in the string. And the original language says that the A's have to be the same as the B's have to be the same as the C's
Oh.
in terms
A
of
to
quantity,
the
so
N,
we.
A to the N, C to the N.
Yes, it's A to the N, B to the N, C to the N. Have we seen that string before? Or that, sorry, that language before?
More or less.
In fact, we proved that it wasn't context-free via the pumping lemma. So if you can find, given a query language, if you can find a regular language where if you take the intersection of those two languages, you end up with a language that you've already proven is not context-free, then you can use that as the contradiction that says that this query language is not context-free. So the intersection is A to the N, B to the N, C to the N. We've already shown that that's not context-free. So if the original example language were context-free, then the result would be context-free. Since the result is not context-free, then the example language cannot be context-free.
The form A to the N, B to the N, C to the N does. It seems slightly different, maybe correct me if I'm wrong, but like it does seem like it relies on a certain form of A's followed by B's followed by C's. So, which seems different than A star, B star, C star, because then you can just kind of,
It is different,
okay,
but the intersection of those languages, we're placing an additional restriction
okay,
on the number. We're saying that all the A's have to come before all the B's, have to come before all the C's, and there have to be the same number of each of them. So to be able to take the restrictions of the first set and the restrictions of the second set, and now all strings that adhere to both restrictions, you'd end up with the strings of A's and B's and C's that come in the order, all of the A's, all the B's, all the C's, and all of them have the same number. Which is the language A to the N, B to the N, C to the N. So this is one way to skirt around the pumping lemma.
Would I be able to ask you to go back to the last one, because I was a little unsure with what you were talking about with the intersection? For that one, what that is an intersection with or,
Yeah,
yeah, what the regular language is, the intersection. with.
yeah, so we know A to the N, B to the N is context free. If we were to identify something that's N is not equal to 100 or is equal to 100, we'd be able to do the is equal to 100 really easily with a DFA. You'd be able to do that. And we learned that the complement of a regular language is also regular. So you can easily complement that language if N is equal to 100 to say N is not equal to 100, in which case you could just invert the finality of the states
Okay.
along the way. Yeah, that'll get you there. Other questions about either of these examples? So this is very nice. I dislike the pumping lemma as much as you all do. It's just not fun. You don't want to do it unless you have to. So this is a way to just think about a problem and come up with a fun solution. There are some limitations to kinds of algorithmic questions that we might want to answer. And the first one is that if you had two grammars and you wanted to figure out, do these grammars produce the same language? No algorithm exists to be able to do this. It's very easy to prove that they don't. You just find a counterexample. Here's a string that one grammar generates that the other grammar does not. And you can use the CYK algorithm to, in cubic time, determine that a grammar can produce a string or a grammar cannot produce a string. So you would just do that process for one grammar and the other grammar, and you would see that sure enough, for a particular string, there's a difference in acceptance. Great, these grammars aren't the same. They don't represent the same language. But if they do generate the same language, then you need an infinite number of strings of comparisons to be able to say that they generate the same language. We're never going to reach that point, so we can never conclude it. You would need to have some way of converting one grammar into the other grammar, and we had a way to do that with regular grammars. We could convert a grammar into another grammar, but the rules of context-free grammars make that process impossible. We can change the form of a grammar, we can convert it into Chomsky normal form, but we can't convert one grammar in an arbitrary form into another grammar in an arbitrary form. At least not without considering all possible grammars, of which there are an infinite number. So that won't terminate either. So that's the big limitation. It'd be very nice if we could be able to answer that question efficiently. So there we have it, my last few final thoughts on context-free languages. We're done with them, aside from, the associated homeworks. We're done with them in lecture, at least until we go back and talk about compilers. The course is supposed to be all the time and compilers, but we couldn't change it. But yes, yeah. The idea is there's a lot of theory behind compilers, and I can't wait to actually talk about their construction because it's cool. But it's gonna be like a last 2 weeks of the course kind of thing, because we just don't have time. So we're gonna start talking about Turing machines, and Turing machines are one of the most interesting and well-studied parts of computer science theory. They're amazingly cool. So we've seen two different classes of languages. Really, we've seen a little bit more than this. We saw the deterministic PDA class of language that was a subclass of context-free. But we're now going to look at a different class. The only difference between the actual state machine representation of this was that the context-free version had a stack and the regular version did not. Other than that, basically all of the rules were the same. You could transition the same way, you had states the same way, acceptance and rejection was the same, the initial state idea was the same, so everything was basically the same, except that you had a stack. So you had to define the stack's transitions, you had to define what it meant to be able to accept with something like the stack must be empty. The question that I have is, are there more powerful language classes? What is an NPDA missing? Think about the difference between what you could program in your programming language of choice and what a non-deterministic pushdown automata could accept. What kind of storage could we use if we wanted to include even more languages? We could use more than one stack.
Maybe a queue.
A queue, it's equivalent to two stacks. We can emulate two stacks with a queue and a queue with two stacks, but yeah, we could shorthand that a little bit by making it a queue. Any other ideas? What other storage structures could we use? Use something like a tree map or a hash map or any of the other structures that you covered in data structures or algorithms or wherever you've heard of them before. You could use a heap, you could use any storage structure. Does it increase the flexibility of the languages that you can represent if you do that? The answer is not meaningfully. So how can we push this? What if we needed to design the most powerful possible automata? What would that look like? How could you design a state machine that had the same level of power as any modern programming language? In a state machine form. It turns out the answer is relatively simple, and it's kind of the first shocking, really shocking thing about this class, I find, is that something that is so simple can emulate any modern program. You write a program in Java or in Python or in C#, and this state machine can emulate the program that you write with just its rules. So let's talk about the standard Turing machine. The storage is a single one-dimensional array, infinite in both directions. So you can imagine being at a particular place on an input tape on a one-dimensional array that can be slid infinitely in either direction. Each cell of that array holds a single symbol. So if we were dealing with a language that had A's and B's, there would be either an A on a cell, a B on a cell, or what we're going to call a blank on a cell, which means the lack of information. It's kind of the empty. This automata is going to be able to both read from and write to this one-dimensional array. So now rather than just reading from the input, it's now a read-write device. So we can write to the input if we want to. We can modify the input as we go. So no restrictions on only moving left to right like we had with every other form of automata we've covered so far. We always had to parse from left to right and we couldn't go back. With a Turing machine, we can go in both directions arbitrarily, at will. There's no other input or output device, so we're not reading from any other file. We're not keeping track of any other storage. We're not taking a stack with us. We're not taking a hard disk with us. There is no other way to write information other than directly on this array. We're going to start calling it the tape. Before we begin the program, all input is going to be on the tape. And it's the read-write head, which is basically how we're going to figure out where we are on this tape. That is going to be positioned at the leftmost part of the input, wherever that happens to be. By the time the program terminates, all output that is relevant to the program will also be written on the tape. Once the program completes, the Turing machine will enter a final state and what we call halt. So basically, here's how we're going to visualize a Turing machine. The brain of a Turing machine is the control unit. That's what's going to keep track of what state it is in. So we're still going to have states like Q0, Q1, Q2, what state we're in, and the drawing that would be associated with that would be within the control unit. The control unit also has a read-write head that has a particular position on the tape. We do not label anything on the tape, so there are no indices to this. So it cannot be, you cannot have instructions like go to position 20. You can only move left or move right. Any questions about this diagram? Yeah,
Just go back one slide real quick.
yeah. Question?
So there's no manipulation. There's no like, sorry, so there's no dynamic, I guess that's not probably the. I guess that. But there's no dynamic operations on the tape in the sense of like, you can't. Before, so like before the Turing machine, quote unquote, is on, there's data or input on the tape.
Yep,
When the Turing machine is on, it can put things onto the tape and then, but it cannot take new information from the tape and then like, it can't just like take something, put something down, take something, put something down. It all has to happen in like,
oh, it absolutely could.
oh,
Read the information, change it, read the information, change it. It could also read the information, move to a new portion of the tape, change something there, go back, read something here, go over there, make an associated change. So it has full dynamic behavior. I think using that definition of dynamic, it can dynamically adapt to what's on the tape, but it all has to be defined within the Turing machine's program, within those internal states and transitions, what it does when it sees those associated characters on the tape. Just like before with automata, it had dynamic behavior as it read the input characters. It was defined by those transitions. It wasn't intelligent in any sense. It was just following the program, the states, and the defined transitions between those. We'll find that that's exactly the case here. We have to define all of those transitions and what happens, which makes writing a Turing machine program really laborious. It's very labor intensive, it's very mentally taxing, but it has the same power as a modern computer, which is wild. There's nothing that a computer can do that a Turing machine cannot. We'll look at the formal definition very briefly, lots of symbols on the screen. Let's see if we can figure out what they are. Just like before, we're going to have a set of internal states in the control unit. This is just your Q0, Q1, Q2. We have the input alphabet. This is everything that could exist on the tape prior to the Turing machine beginning. We have the tape alphabet, which is kind of the same as the input alphabet, except there's also this concept of a blank. You can see that the blank is a character in the tape alphabet. So this is just everything you might see on the tape, including the blank symbol, which is not part of the input alphabet. So the blank is not part of the input alphabet. You can't have a string with a blank in it, but the blank on the tape means there is no information here. Think of it kind of like the null character. It's not the empty string, it's the straight up null character. It's the lack of a character. We define of the internal states, we define an initial state. Any of the states can be final states. What changes is the transition function, this delta. The input for this is going to be a product of the internal state and some kind of tape alphabet. So it's going to look at what's currently on the tape. That paired with the internal state is going to tell us what to do. So what's on the tape combined with what state we're in defines how we're going to behave. And then as a result of this, the actions that we take from that particular state is that we move to a new internal state. Could be the same state. So we have a transition just like we've had in every other automata from state to state. We're going to write something on the tape. It could be exactly what's already there. It could be something that's completely different. And then finally, once we're done with that, we will either move left or we will move right. We cannot stay in the same place. So that means move to the next leftmost element of the input tape or move to the next rightmost element of the input tape. To give you an image, we have some kind of internal state. This defines a particular transition. So we start in state Q0 and we look at the tape. If at the current position of the read-write head, there's an A on the tape and we're in state Q0, then it says transition within your control to state Q1. write a D on the tape at the current position and move right to the next rightmost thing. So you see the difference between part A and part B here is that we wrote to the tape, replacing the A with a D, which is defined right here. This is what's written to the tape. We moved right, so now the read write head is positioned to the right. So we've changed the tape ABC to DBC. Maybe there's a reason for that. There's probably a reason for that somewhere in the program, but that is what a transition looks like. Question?
Use the word rightmost. My brain wants to say it's like the most right thing that we have that exists on the tape, which doesn't make sense, but it just means move one space to the right.
Exactly. Yep. You can only move one space left or one space right. We'll talk about different models of Turing machines later where we relax some of these restraints, but it turns out, and we'll talk about this, that a lot of these simple changes you can make to Turing machines don't change what a Turing machine can do. So we want to define it as simply as possible with as few possible moves as possible to get that same behavior. So the simple Turing machine is meant to be as intellectually simple as possible, having as few possible moves as possible. And I'm not saying at all that it is simple. It's just that if I added things like more options of things that we could do, it's going to make it much harder to write a Turing machine program for it. Yeah,
Pop back, one slide.
yeah. So not too many changes from the push down automata, but enough that since we're dealing with the input tape, we can write in addition to read. The reading and writing happens in the same place, and we move locations within the input/output, either one space left or one space right. Those are the big changes. Questions on either the formal definition or this example transition? So in order to transition, we need to care about two pieces of information: the state that we're in and the character that is on the tape at the current position of the read-write head. That dictates three things: the new internal state, the character that we write at the current position of the read-write head, and the new position of the read-write head, either to the left or to the right of the old position of the read-write head. You can now start to think of them not so much as language acceptors, but as a simple computer. We've now created enough power in our automata to be able to do more than just accept or reject strings in a language. And accepting or rejecting strings in a language is a very important concept to computer science, but eventually we want to be able to write programs that make changes to things, not just say yes or no to some question. So thinking of the components of a computer, we have a processing unit with a finite amount of memory. Think of it as cache. The memory is just the internal states of the control unit. The tape is our secondary storage. You can think of this as either RAM or hard disk space that has unlimited capacity. We need this to be able to get some theoretical results, like what is computable if you have an infinite amount of RAM or an infinite hard disk. While we made this as simple as we possibly could, the actual instructions are quite limited in scope. So if you're thinking of this as some kind of AI with sensors, what can it sense about the world around it? It can figure out, all right, what's on the tape at the current position. Given that information, it can decide what to do next. Things it can do: rewrite the symbol of the current position. Change the state of the control unit. And move the read write head to a new position. So those are the actions it can take. That's the one sense it has. All it can do is figure out what state am I in and what's on the tape at this exact position. No other information is needed. Given this definition, do we think that a simple Turing machine is deterministic or non-deterministic? Interesting. What makes you argue that it's either deterministic or non-deterministic?
Well, every state or every read has to have some sort of defined. Much like a computer has to have a defined definition of what it's going to do.
What I've described so far is absolutely deterministic. But there's nothing that says that we can't construct a non-deterministic Turing machine. But yes, we're going to start with thinking about this in a deterministic world, because while we could create one that is non-deterministic, as we start to write Turing machine programs, it's much easier to ground yourself if you think deterministically. So the transition function, if we look back at the transition function, defines at most one move for each configuration. Remember that configuration is just a tuple of the current state and the current input symbol or the current symbol on the tape. Think to yourself about what the limitations of that Turing machine might be. Intuitively, I've already spoiled that it's the same as a modern computer, but rather than just accepting that blindly, think about, is there anything you can think of that a modern computer can do that a Turing machine cannot? Because I want to address those and try to come up with ways that we can think about Turing machines that are able to do complex things. Yeah,
I'm thinking about like external input output devices like a mouse or a keyboard where you're like doing separate things to the program that it might not.
could you register that on the tape or have something that writes that on the tape?
I guess can the tape be? Yeah, I guess it would just be part of the.
Think of the tape as just data. If anything that we can represent as data, we can put on a tape. So if that's the position of the mouse cursor, if that's whether the mouse is clicked or not.
Yeah, it gets weird because when I'm thinking about the Turing machine, I'm not assuming that it would probably to be able to do these things, it would be doing like millions of operations every
Yes.
second when it was.
Yes. It's about kind of the abstraction of this, what is possible, not necessarily how many computations. I mean, if you think about the sheer number of computations that a computer is doing as you move your mouse, it's a lot. If you actually look at the number of CPU operations that are happening as you do anything that is mundane on a computer, there's a reason that it can handle 1 billion calculations or more per second. If you can think about what would 1 billion moves on a Turing machine, what would you be capable of with 1 billion moves? That's quite a bit. So let's start thinking about how can we write Turing machine programs? The Turing machine begins with the control unit in its initial state. We'll call that Q0 for the moment because that's what we've been using throughout the quarter. We know there's some information written on the tape. We're just going to go transition by transition based on that. Remember, it's deterministic, so there's only one path for it to take. There's only one thing that it can do in any particular control unit state for a particular character that's on the input tape. Keep in mind, though, that it might be changing what's on the tape as it goes. And that may change the associated behavior during runtime. So whenever we see a program that can change or adapt during runtime, it's very similar to the Turing machine rewriting some information on the tape and then using that new information on the tape to adjust its behavior on the fly. As long as all of that has been predetermined. Like there's nothing that we can program that's not predetermined, right? There are runtime decisions that we can make that change how the program works, but there's nothing that hasn't truly been predetermined. It's one of many predetermined processes. If you are inheriting from a class, you can only instantiate something that's one of the subclasses, even though we haven't defined it at compile time. At runtime, we know what the subclass is. So it's one of a predetermined set of possibilities. So we could represent that with a Turing machine. You rewrite a symbol to be another symbol, and then when you come upon that symbol, you act on it based on the new symbol that you see. So it's not the same as it was at the beginning, but it's all predetermined. Eventually, through some deterministic process, the Turing machine may decide to halt, which means that it accepts in a final state and has nothing else to do. There's always a special state in the control unit called the halt state. So whenever you would reach a final state in a particular thing, the last thing you do is transition to the halt state. It basically says we are done. So this occurs when the Turing machine reaches a final state. Great, now halt. If there's a transition that's not defined, we halt and reject. So note that you do not need a total function like we did in a DFA. This can be a partial function if something is not defined, like it was in an NFA, then we don't care. We're going to just stop and reject. No total function necessary. With the last couple minutes of class, I'm going to give you a basic example of a Turing machine program. Here's the Turing machine definition, and here are the associated transitions. So this is a basic Turing machine. Take a minute, see if you can understand what this is telling us.
Does it take in a string of A's and B's and turn it all into B's?
So yeah, it's going to be replacing A's with B's, keeping B's as B's, only going from left to right through the input string. But yeah, we have two internal states, Q0 and Q1, of which Q1 is a final state. If we reach Q1, we are done. The tape, the input alphabet is AB, the tape alphabet is AB and blank. Blank would just represent that there's no more input to be read, basically, in this case. The transitions say that if we're in state Q0 and see an A on the tape, we're going to stay in state Q0, change the A to a B, and move right. If we're in state Q0 and see a B on the tape, we're going to stay in state Q0, replace the B with a B, so make no change, and go right. If we're in state Q0 and we see a blank, which means that we've reached the end of the input, then we're going to transition to state Q1, write a blank over the top of the blank, and move back left to the last position in the string, and go into a halting state. So we've moved from left to right, replacing any A's with B's, leaving any B's alone, changing the string to be all B's. So now if we have this associated tape here with a couple of A's on it, we can see that we start in state Q0 and we go through this process. We're in state Q0, read write head is pointing at the first A. We have a transition defined for that. It's the first transition. It's this transition right here. We're gonna say C to A, replace it with a B, move right. So then we reach this position where we've changed the A to a B. We've moved from the first position to the second position. We're still in state Q0. So we're gonna do this transition again, where we replace the A with a B and move right. Now we see a blank here. So we're gonna transition from state Q0 to state Q1, rewriting the blank with a blank and moving back left. We reach a halting state, so we are done. We are out of time. Anyone have any quick questions I can answer about this? Yeah,
So there's no indexing on this, but you'll obviously have a place that we must start on the tape.
yeah,
So-
you have a position to start. It's kind of where you place the read write head at the beginning. It's
Okay,
at the leftmost part of the input.
Can a tape have a space like AA blank AA in it?
Yeah, you just have to define what to do when you see a blank. Maybe you want to move right instead of left. And that's where you should say, when you see a blank, keep going.
Okay, that makes sense.
Even if I want to say, if you see two blanks in a row, then do something else. Yeah, you can absolutely add spaces, add whatever you want.
What? I'm not totally sure how to work with the part. Like, where will they take move to, if at all, when? Like, if we didn't define that, you said if there's all stage,
Yeah,
what happens then?
it rejects in a halt state. So basically you get it halted in a final state, halted in a non-final state.
I mean, so does the tape just like get burned, or?
It's a clear manual tape. No such tape exists, it's infinite in both directions.
Okay.
So you can think of it just as it can be any physical thing with limits. It can be any idea with an infinite amount of possible space, but the idea is just not to constrain what's possible by the system.
Is there a way to draw that out?
I
represent it in one of these little diagrams, or is it just kind of like
At
at that
I didn't
moment,
know
sort of just burn the tape and leave it as is?
Yeah, it needs to be.
Not a single.
It's not necessarily done, maybe it's created an output file, and now we can go read the output file to see the results of the program.
Okay,
The input tape at that point is basically just the storage of the output of the program. The changes that it made are associated with what did the program do.
so we would just say that we would leave the tape completely as is and then put a little asterisk next to the file that says this wasn't completed, terminated.
Okay.
Yeah,
Yeah.
it stopped at a non-final state, so it would reject. We get that acceptance or rejection signal as it terminates.
Thank you.
Yeah, it's cool. See you all tomorrow.
I have these